Hi everybody, my name's Christopher Collison and I'm going to be talking to you today about making some dilutions and converting from grams to moles and into moles per liter, which would be the units of concentration. And we're going to use a lot of these calculations in all of the experiments that we find in this particular course. So let me show you some slides and we'll work through some examples. So what we need to remember here is that this is a presentation on some true foundations of chemistry, and what we need to do is recognize that in this case we're going from grams to moles and from moles into a concentration, and that concentration, by the way, the units I'm going to refer to frequently for concentration is going to be moles per liter. We often use this capital M term in here as a unit of concentration, which would be molar, but I find that it's much more instructive to use the equivalent set of units, which would be moles per liter, and we'll see why as we go through the rest of this presentation. So all in all, we can boil down the foundations of quantitative stoichiometry to the following graph. And what we often find when we're doing quantitative stoichiometry or quantitative chemistry, let's suppose we start with a reactant A, and we usually in a lab scale we have measured this out on a balance, so we have the mass of that particular reactant. What we're also going to find is that we are going to be using in this particular course, we may often have a concentration and a volume of that same reactant. We'll see later how we go from a mass of a reactant A actually into a concentration and volume of that reactant A. So what we use in chemistry, of course, is the number of moles, so we're always reacting amounts. And so what we want to do is go and start to prepare a value for the amount of a particular species A. How do we do that? Of course, if we start with our lab based value of mass, right? We've measured out the mass on a balance. If we have that mass and we want to get the number of moles, well, we simply divide that mass by the molar mass, and that's going to give us the amount in moles of that particular species. The other thing, of course, we can do if we have a concentration, if we end up having a concentration and a volume of a liquid, obviously it makes a lot of sense to work with solutions because we can mix these solutions very readily. But if we want to know how many moles of a particular species we have, then the other thing we recognize is the amount. Well, that's in moles in here. That's equal to the concentration. The concentration is in moles per liter. And of course, we can multiply that by the volume, and the volume is in liters. So those liters cancel, and that's how we end up with the number of moles of our reactant A. If we go on to think about doing some more complicated yield measurements, which will happen at some point in this course, we may need to put forward a chemical reaction, a chemical equation. Then we would use the coefficients of that chemical equation, and that would allow us to perhaps tell how much of a product B, how many moles of a product B we've obtained from a given limiting set of reagents A. Okay, so how much B we get, we can do another calculation for that. And of course, if we want to get back to the yield, the amount of mass of a particular reactant B actually this should be a product in here, maybe a product B. So if we want to know the mass of a product B, then we take that number of moles and then we multiply that number of moles by the molar mass. Of course, now we've got grams per mole multiplied by the number of moles, and those moles now cancel, and so the answer will end up being in grams, and that's the amount of product B that we'll end up with. Of course, we can also do some similar work with solutions. And so if we end up with an amount of a particular product B in terms of moles, we also recognize that when we have a number of moles and we divide that number of moles by the volume of the liquid that we have at the end of that reaction, well, that's actually going to give us, in fact, that is our units right away. In moles per liter, that actually is going to give us a concentration. Of course, we already have the volume, so this leads us to our final answer here of concentration and a volume, and that again should be the product B. So let's just think about this through a little bit. Let me just make sure it's clear what I've said. So the molar concentration is how we describe certain solutions, and we define the molar concentration in the following way. We talk about the concentration or the molarity in here, and the molarity is defined, or the concentration that we care about is defined as moles per solute, liters divided by liters of solution. In fact, this is a unit, this molarity here. Capital M is our unit, and it's defined as shown up here as moles of solute divided by liters of solution. This is a unit, in fact, of concentration. So let's look at some examples, and let's put some chemistry to the test. So I've titled this particular slide, Solutions, a Convenient Way to Combine Reactants in Many Reactions. And here's a problem that we'll work through. The question states, how many grams of silver nitrate are needed to prepare 250 milliliters, so this is a volume, of 0.0125 molar silver nitrate. And again, that molar, what we can do is we can recognize that that is simply equal to moles per liter. So how do we calculate the solution? So we're looking for grams, but what do we have initially? Well, what we've got in here is we've got a volume. The volume that we need to obtain is 250 milliliters. Of course, that's equivalent to 0.250 liters. We're also told the concentration that we need, and the concentration that's given to us is 0.0125, and that would be molar. I'm going to write it in terms of moles per liter. Why? Because if I know that concentration, I know my units are moles per liter, that actually helps me write and remember the key equation. Concentration here is equal to amount or number of moles divided by volume. Okay, so in this particular case, if I want to know how many grams of silver nitrate are required, how many grams are required, well, how do I get grams? Well, what I need to find initially is the number of moles. So what I'm looking for is a number of moles. So that number of moles is simply, we do some simple algebra. We'll bring the volume over to the other side here. So the number of moles is simply equal to the concentration multiplied by the volume. And this will be an important equation that will help us in the next few slides. Let's calculate that number of moles in here. So that number of moles is going to be equal to the concentration. So that's 0.0125 moles per liter, and that's multiplied by the volume, which is 0.250 liters. And that comes out to be, if we throw that into the calculator, that comes out to be 0.003125, and that unit there is moles. Notice I've got 4 significant figures here. At the moment, I'm not justified to use 4. I've only got 3 significant figures earlier in my slide. I'm only provided with 3 significant figures. But for now, I'm still not complete with my calculation, because we have to remember, what am I looking for? I'm looking ultimately for the number of grams. That's what the question is asking me to find. So now all I need to do is convert this number of moles into a number of grams of silver nitrate. How do I do that? So let's bring forward the answer from the prior section. So that was 0.003125, and that was moles of silver nitrate. If I have a periodic table handy, of course, I can look up the atomic weight of silver, and we find the atomic weight of silver, and we find that the atomic mass of nitrogen is 14.01. There's one nitrogen, there's one silver. There are 3 oxygens in here. So what I'm going to do, of course, oxygen has an atomic weight of 16.00. There's my oxygen atomic mass. So what we're going to do is there's 3 oxygens, so that leaves me to a number which is 48. 3 times 16 is 48. Basically sum these all together, the answer ends up being 1.69.9. okay, so it would be 0.87, but 0.9 for significant figures is still fine here. We're ultimately going to cut this down to 3 significant figures. What are the units? This is grams per mole, and when I use my units as grams per mole, then that becomes helpful to me because it tells me, in fact, how I'm going to calculate the mass of the silver nitrate that I need to weigh out on my balance. So I'm going to put that all together. 0.003125 moles, and I'm going to multiply that by 169.9 grams per mole, and then of course we note that the moles will cancel, and my final answer is going to be 0.531 grams of silver nitrate. Finally, I'm going to use 3 significant figures here because I was only provided 3 significant figures in the values at the start of the problem. So let's switch gears here a little bit and focus on something that will be used frequently, time and again, in Chem 155, and that is we're often going to have or be provided with a stock solution of a particular reactant. We may be asked to work with a stock solution of a dye that we need to do some spectroscopy with, or a stock solution of a food coloring that's in a sports drink. What we have to recognize is that we can dilute a stock solution, a high concentration of solution, and make solutions of lower concentration that serve us better in our particular experiment. So the equation that we're going to use in this particular section is one that will come up time and again. One way of describing it is the volume of, in this case, the dilute solution multiplied by the concentration or the molarity of the dilute solution is equal to the volume of the concentrated solution multiplied by the concentration or the molarity of the concentrated solution. Why does this always work? We have to conserve mass in chemistry. If we take a volumetric flask and we take a small aliquot, and that aliquot that we put in is our stock solution, the number of moles in that stock solution is V concentrated multiplied by the molarity, M concentrated. When we take a volume, and that's in liters, and we multiply it by a molarity or a concentration, that's in moles per liters, then when we cancel these liters out, we end up with a value in moles. So when we take an aliquot of a stock solution and we put it into a volumetric flask, here's our solution. This is the number of moles. If we simply add water to it to dilute it, we're only adding water. We are not ever changing the number of moles that are in that solution. So if we remember that, then we will always recognize our fundamental equation here. Another way of writing it, by the way, is C1 V1 equals C2 V2, where the C represents a concentration and the V represents a volume. What do we get? If we multiply a concentration by a volume, we get a number of moles. So there's the theory. Let's put this equation into some practice.